table for each process. A pointer to the page table is stored in the process control block. When the dispatcher is told to start a process, it must reload the user registers and define the correct hardware page table values from the stored user page table. The hardware implementation of the page table can be done in several ways. In the simplest case, the page table is implemented as a set of dedicated registers. These registers should be built with very high-speed logic to make the paging address translation efficient. Every access to memory must go through the paging map, so efficiency is a major consideration. The CPU dispatcher reloads these registers just as it reloads the other registers. Instructions to load or modify the page table registers are of course privileged, so that only the operating system can change the memory map. The DAC PDP-11 is an example of such an architecture. The page table consists of 8 entries that are kept in fast registers. Most contemporary computers allow the page table to be 1 million entries. So the page table cannot store into the registers because it is too large, 1 million entries. So it can only store in main memory. Okay. If the page table is very large, the page table is stored in main memory. And the hardware will increase 2 special registers for this purpose. One is page table base register, points to the page table, the starting address of the page table in main memory. And the second special register is page table length register, indicates the size of the page table. And the value is checked against every logical address to verify that the address is in the valid range for the process. So here, these two are the special registers for paging memory management scheme. And this is the logical address. And we can see the higher 4 bits are the page number, and the lower 12 bits are the page offset. The hardware first used the page number, logical page number, to compare it with the page length register, and find that if this page number is smaller than the page length register, it is valid. Otherwise, it is invalid, and the hardware will check to the operating system. It is a fault, so this is addressing error, and the operating system will terminate the execution of the user process abnormally. And if the logical page number is valid, then the hardware will use the page number and the content of the page table base register and add them together to find the page table in the main memory. You must know this page table is in the main memory. And find that from this page table, find that logical page 2 is stored in physical frame 8, and replace the logical page number with the frame number, and we get one-dimensional physical memory address. This is physical address, and use it to access the main memory and fetch the data or instruction. Okay, so this is the address binding step. Okay, changing page tables requires changing only these two registers, reducing context switch time. So we find that when the dispatcher is told to execute another process during context switch, the operating system has to reload the contents of these two special registers. The contents for these two registers are stored in PCB of each process. So every time during context switch, the operating system will reload these two special registers. But the page table for each process is stored in main memory. Okay? So in this scheme, every data instruction access requires at least two memory accesses. So the first time is for accessing page table to find the physical frame number. The second time is for data or instruction. Okay. The two memory access problem can be solved by the use of special fast lookup hardware cache called associative memory or translation look-aside buffer. The TLB is associative high-speed memory. Each entry in the TLB consists of two parts, a key and a value. When the associative memory is presented with an item, the item is compiled with all keys simultaneously. So you must know the associative memory works in parallel, so it is very fast, different from the main memory. Okay, if the item is found, the corresponding value field is returned. The search is fast. Okay, and if the item is a TLB lookup in modern hardware is part of the instruction pipeline, essentially adding no performance penalty. To be able to execute the search within a pipeline step, however, the TLB must be kept small. It is typically between 32 and 1024 entries in size. The TLB is used with page tables in the following way. Okay, let's look at paging hardware with TLB. When CPU executes instructions, during its execution will generate a logical address, and the address translation hardware will break one-dimensional logical address into two parts according to the size of the physical frame. The lower end is the page offset, and the higher end is the logical page number. And this logical page number now is passed to sent to TLB and compiled with all items simultaneously or in parallel with all items. If TLB hit, that means this logical number is in the TLB, and we say TLB-H. Then we can find the corresponding frame number, and we will replace the logical page number with the physical frame number, and we get one-dimensional physical address and a size physical memory. Okay, so we see if TLB-H, there is only one main memory size. Okay, in this picture, without TLB, we say one memory size requires at least 2 times physical memory accesses. Okay, but with TLB, if TLB hits, then 2 memory accesses reduces to only 1. Okay, but here, if the comparison doesn't find the page number, that means TLB miss, then the hardware has to use the logical address to access the page table in main memory, and find the corresponding physical frame number. Also has to reload this atom into the TLB. Okay, and at the same time replace the logical page number P with the physical frame number F, and get the one-dimensional physical address and a size physical memory. Okay, here because when TLB miss, just now we say the hardware has to reload this item into TLB. So there is problem. If at this time the TLB is full, the operating system must select 1 for replacement. So this involves replacement algorithm. Replace policy range from least recently used to random. About this algorithm, LRU, we'll learn next chapter. Okay, so here I will omit it. Furthermore, some TLB allow entries to be wired down. Okay, where that means when replacement happen, this atom will not be replaced, meaning that they cannot be removed from the TLB, such as entries for kernel code. Okay, so this is the address binding was TLB. Okay, some TLB store address-based identifiers in each TLB entry. And ASID uniquely identifies each process and is used to provide address-based protection for that process. When the TLB attempts to resolve virtual page numbers, it ensures that the ASID for the currently running process matches the ASID associated with the virtual page. If the ASIDs do not match, the attempt is treated as a TLB miss. In addition to providing address-space protection, an ASID allows the TLB to contain entries for several different processes simultaneously. This is the important. If the TLB contains the page entries for several different processes, then we must add 1 column for TLB. That column is for the process ID. Here it is coded address space identifiers, ASID. Okay, so If the TRB doesn't support separate SD, then every time a new page table is selected, the TRB must be flashed to ensure that the next executing process doesn't use the wrong translation information. Otherwise, the TLB could include old entries that contain valid virtual addresses but have incorrect or invalid physical addresses left over from the previous process. The percentage of times that the page number of interest is found in the TLB is called the H ratio. An 80% hint ratio, for example, means that we find the desired page number in the TLB 80% of the time. It takes 100 nanoseconds to access memory. Then a mapped memory access takes 100 nanoseconds when the page number is in the TLB. So let's associative lookup. That means the accessing time for TLB is 20 nanoseconds. Well, assume